Hello. In this video, we learn about analytically computing the absolute maximum of a function. In circuit analysis, oftentimes we need to compute the value of a particular element, for example, a resistor, to maximize the power transfer to a load circuit. And we can write down the power as an equation of this parameter. So if I have this equation, the question comes, can we analytically solve for the value of this parameter that maximizes this equation? The answer is yes. This is the main topic for today's video. We would like to learn the basics of finding the maximum of a continuous function, knowing that this function is twice differentiable over a domain D. So let's reflect on this figure here. The general definition of the absolute maximum value is that it is the value that no other value in the function is larger than. So for this function, we have the input x, the output y, which is equal to f of x. Here we have the function computed at point E is larger than any other point into our function. So here we say that f of E is the absolute maximum of this function over the range over which this function is defined. So now we have the question, if I graphically have the function, I can look and say, okay, hey, this is the absolute maximum. But what if I couldn't plot this function? Is there a way to analytically solve for the maximum? The answer is yes. Let's reflect on this figure here. And one thing that characterizes this maximum is the slope at this maximum point as 0. So at the maximum, we have a slope 0. But wait a minute, the slope also here is a 0. So what is the difference between these 2 points? So this point here is our global or absolute maximum. And this point here, we call it as a local maximum. So both local and global maxima will have a slope of 0. If we note more, this point 2 has a slope of 0, but this point here is a local minimum. So what we can conclude here is that at the extrema of our function, i.e. maximum or minimum, we're going to have a slope of 0. So is there any way to differentiate between what make a maximum and what make a minimum? The answer is yes. So far we have looked at the points that give us a slope of 0. But this gives me candidate points that can be either global maxima, local maxima, or global and local minimum. Okay, so those are the local extrema points. It can be either maximum or minimum. Out of these points, we can use the second derivative. If the second derivative is less than 0, this means that we have a maximum, either global or local. So far, to get our candidates for the extrema points, we're going to compute the slope, which is the first derivative, and find those points at which we have a slope of 0. This gives me the local extrema points. From those local extrema points, we're going to compute the second derivative and only pick those points that give us a negative second derivative, and those correspond to local maxima. Finally, to know which one is the absolute maximum, we are going to compute the function at every location that is a candidate for a local maximum. Also, we are going to compute the function value at the end values of the domain, which is the lower and upper end for the input. Now we have all those values. We look for the highest value. We say, okay, this is our maximum, our global maximum. So in summary, we can summarize the process of finding the absolute maximum over 5 steps. So step number 1, we are going to find all candidates for local extrema. which is local maximum and minimum, by computing the first derivative and find those points x at which the slope is 0. So those candidates are maximas and minimas. So to pick the maximas, we are going to compute the second derivative and only pick those points that give us a negative second derivative. Okay, so now I have all the location of local maximas. Okay, I need to identify the location of the absolute maximum. So we are going to compute the function of f of x at those location corresponds to the maximas we obtained from step number 2. We also compute the function at the end of its domain, which is the upper and lower value of the input. Now we have the value of those functions. We look for the maximum value, and this gives us the maximum value and its location. So let's apply that on a couple of examples. So for this example, we have a function, a second order polynomial, and we'd like to find the location that corresponds to the absolute maximum. Here we are not explicitly given the range, so we can assume that the domain of this function is from -infinity to infinity. So step number 1, we are going to compute the first derivative, f of x. So for this function, the derivative would be 20 minus 8x. And then solve for the value of x such that this equation is equal to 0. Apparently, we can find that from here, from this expression, x is equal to 20 over 8, which is 5 over 2. So here we have only one candidate, and we don't know whether this candidate corresponds to a global maxima or a minima. So we are going to compute the second derivative. So computing the second derivative gives us -8. And since the second derivative is negative for all values of x, including this candidate that we have, so this candidate here corresponds to a maxima. Now we compute the value of the function at x equal to 5 over 2. So this gives us 50. We also compute the function at the end of the range, so f of minus infinity. F of minus infinity give us negative infinity, and the other end of the range or the domain, f of infinity, give us minus infinity. Okay, so now I have the value of the function computed at the candidate for the local maximum and the function value at the end of the domain. Apparently, the highest value is here. So we say that this function is at max value of 50 when x is equal to 5 over 2. So this is the location of the maximum, global maximum, and this is the value of the global or absolute maximum. Okay, now let's see another example when we have more than one candidate. So here we have a quadratic function, and this is defined over a finite range from -2 to 1. We would like to find the absolute maxima and the location of that maxima. Okay, so we start by computing the first derivative f prime of x, which is equal to 3 minus 3x squared, and then find the candidates that make this is equal to 0. So the values of x that make this equation equal to 0 are x equal to -1 and x equal to +1. These are the two candidates for local extrema, local maximum and local minimum. So to verify which one corresponds to a maxima and which one corresponds to a minima, we compute the second derivative. So the second derivative here is equal to minus 6x. Now we compute value of the second derivative at the first candidate, which give us 6. 6 is greater than 0, so this is not a maximum. We repeat the process for the second candidate. If double prime of plus 1, this gives us negative 6. So this is negative. So now this point x equal to plus 1 is maxima. Okay. Now we need to compute the value of the function f of x at our local maximum points, which is plus 1. So this gives us 3 times 1 minus 1 cube. This is equal to 2. Okay, so this is the value of a function at least the local maxima, if not the global. Okay, so to complete the solution and verify either this is the global maxima or the local maxima, we are going to compute the value of the function at the interval or the range points, end of the range. So we need to compute f of minus 2. So f of minus 2 give us 2 minus 2 times 3 minus 2 cube. This is equal to negative 14. And compute the function value at the other end of the range, 1.5. So this gives us 3 times 1.5 minus 1.5 cube, and this is equal to 1.125. So what we did now, we had two candidates for local extrema. We rejected one. This is not a maximum. We accepted one. Okay. We have the value of the function at this candidate maxima. We have the value of the function at the end of the range. Apparently, you can see that this is the maximum. So the maximum of f of x is equal to 2. And this happened at a value of x equal to plus 1. So, yep, that's it. This is how we compute the maximum of a function. We take the derivative equated to 0, we get the candidate, then we use the second derivative to accept the candidate for maxima or reject it, and then we just double check with the end of range points to make sure that the end of range doesn't have any maxima. Okay, and now we have the three numbers, 2 minus 14 and 1.25. Apparently this is the highest, so this is the maximum value, and this occurs at a value of x equal to plus 1. Thank you.